In the previous lecture, we introduced a number of important notions and concepts like linear dependence, linear independence, subspace in the coordinate space, a basis in a subspace, and we proved some important statements about these objects. And today we will continue to study their properties, and then we will introduce the notion of the rank of a matrix. But first we need to discuss one very important example that will be used in the proof of one of the theorems. So 4.5, the dimension of a subspace. Example. Consider the coordinate space Rn. So this space can be considered as its own subspace, right? And so let us prove that the vectors of the form 1, then zeros, 0, 1, and then zeros, etc., and 0, 0, and 1 in the end. So let us prove that these vectors form a basis in the coordinate space Rn. Of course, this is more or less obvious, but let us give a formal proof of this statement in order to show how formal proofs of such statements can be generated. So we need to prove that these vectors form a basis, so we need to prove two different things. So first of all, we need to check that these vectors are linearly independent, and then we need to show that any vector from the coordinate space can be represented as a linear combination of these vectors. So first of all, assume that these vectors are linearly dependent. That is, there exist alpha 1, etc., alpha n, so the coefficients alpha 1, etc., alpha n, such that alpha 1 multiplied by the first vector plus alpha 2 multiplied by the second vector plus etc. plus alpha n multiplied by the last vector equals 0. So this relation is equivalent to the following relation. We have the vector of the form alpha 1, alpha 2, etc., alpha n, and this is the 0 vector, just because in each row of these vectors we have only one non-zero element. So we can just write down this as a single vector, and we get the following relation. And so this vector is the 0 vector. That's why all its coordinates are zeros. So for every I from 1 to n. So this proves that this family of vectors is linearly independent. And now we need to express any vector from the coordinate space as their linear combination. So consider a vector x with coordinates x1, etc., xn from the coordinate space. So obviously the following relation is satisfied. So this vector x can be represented as the following sum of these vectors. So x1 multiplied by the first vector plus x2 multiplied by the second vector plus etc. plus xn multiplied by the last vector. And that's why this vector x can be represented as a linear combination of vectors from this family. So I will denote it by a star. So this proves our statement. Now we have a basis in the space Rn that consists of n vectors. And having considered this example, we can formulate and prove a very important statement about the basis in vector subspace in the coordinate space. So the first claim here is that every subspace V in the coordinate space Rn has a basis. Then the number of vectors in any basis in V is the same and is less or equal than n. So there cannot be a subspace with more than n vectors in a basis. So let us prove this theorem. We actually need to prove three different claims. And first, let us maybe start with the last claim. So if there, during the previous lecture, we proved the statement that the number of vectors in a linearly independent statement in a linearly independent family cannot be greater than the number of vectors in any basis. So we know that vectors of the form that we just discussed in the previous example form a basis in the coordinate space. Assume there exists a basis in the subspace V, then this family of vectors is linearly independent as a family of vectors from the whole space. And so it follows from the statement of the previous lecture that the number of vectors in this family is not greater than n, which is the number of vectors in the basis, in a basis that we just discussed. So this proves the third claim, that if there exists a basis, then the number of vectors in this basis is not greater than n. Okay, now let us show that every subspace has a basis. So if V is the trivial subspace, then there are no non-zero vectors in V, right? And the zero vector cannot be included into a basis, so there is only one basis. There is only one basis, that is the empty set. Just because there are no vectors that can be included into this basis, and zero vector cannot be included there. So in this case, though this case is trivial. Okay, if V is not trivial, then there exists a non-zero vector V from V, maybe V1, I'll denote it as V1, such that V1 is not zero. Okay, consider its span. There are two options. So this span either coincides with the whole subspace or it does not coincide with the whole subspace. So if the linear span of V1 is equal to V, then V1 forms a basis in V. This follows from one of the statements of the previous lecture, just because every vector in this case can be represented as a linear combination of vectors from this basis consisting of one element. Okay, otherwise there exists V2 from V such that V2 does not belong to the linear span of V1. It also follows from one of the statements of the previous lecture that in this case vectors V1 and V2 are linearly independent. So consider their linear span. And once again, it is either the whole V or it is some subspace in V. So if V1, V2 equals V, then we have a basis. Otherwise, there exists V3 that does not belong to the span of V1, V2, etc. So we construct these vectors in the following way. Let us note that this procedure cannot be continued infinitely. So assume we have a family a linearly independent family, just because this construction always produces a linearly independent family of vectors. V1, V2, etc., Vk in V. It follows from a lemma from the previous lecture that K is less or equal than n, just because we have a basis in Rn that consists of n vectors. So we denote this basis by a star. We have a basis in Rn that consists of n vectors. Therefore, the procedure of constructing this family of vectors stops either when k equals n, in this case v equals Rn, or when k is less than n, and we get a basis, because in this case there is no vector v sub k plus 1 from v that does not belong to the span of the vectors that we just constructed. So this proves the existence of a basis. So the first claim is also proved. And now we need to show that the number of vectors in all bases in V is the same. Let V1, etc., Vk and W1, etc., Ws be two bases in the space, in the subspace V. Then both families are linearly independent. So apply a lemma from the previous lecture. So we have two families. The first one is a basis, and another one is a linearly independent family. So since V1, etc., Vk is a basis, and the second family is linearly independent, the number of vectors in the second family should be less or equal than k. And on the other hand, since the family W1, etc., Ws is also a basis, and v1, etc., vk is linearly independent, we have another inequality. So we can say that the number of vectors in this linearly independent family cannot be greater than the number of vectors in the basis. So k is less or equal than s. Hence, k equals s, and this is exactly what we need to prove. So the numbers of vectors in all bases in our subspace is the same. So this proves the theorem, and now we can give the definition. The number of vectors in a basis in the subspace V is called the dimension of V. So the notation is dim V. So this is the number of vectors in the in a basis in V. And so let us have just two simple examples. So the first example is the coordinate space Rn. So the dimension of the coordinate space is n, just because we have a basis that was denoted by a star. We have a basis of n vectors. And the second example is also trivial. So the dimension of the trivial subspace is 0 because there are no vectors in a basis of this subspace. So this is the theorem and some very simple examples. And now we will introduce the next notion that is very important for the course of linear algebra, that is the notion of the rank of the matrix. So section 5, the rank of a matrix. .1, the row rank. So let us start with the definition. Let v1, etc., vk be a family of vectors in the coordinate space Rn. Then the dimension of the span of these vectors is called the rank of the family we have just defined the notion of the dimension of a subspace, and so the dimension of this linear subspace is called the rank of this family of vectors. And one more definition. Let A be a matrix with n rows and m columns and with real entries. Then the row rank of A is the rank of the family of its rows. As vectors in the space Rm. So each row has m components, and that's why they can be referred to as vectors from the coordinate space Rm. So the row rank of the matrix A is the rank of the family of its columns. So we can just write down this in the following way. So the standard notation for the rank is just Rk, and so R in the subscript denotes that this is the row rank of A. So the row rank of A is the dimension of the span of rows of our matrix. So row 1 of A, etc., row n of A. And now let us prove a proposition that the row rank of a matrix is preserved by elementary row operations. That's quite simple. So let A be a matrix with n rows and m columns, and assume B is obtained from A by an elementary row operation. Then, if we just recall what elementary row operations we have, we can easily understand that the span of rows of the second matrix, we have n rows, the span of rows of the second matrix is a subspace in the span of rows of the initial matrix. Just because when we apply elementary row operations, we add rows, we multiply rows by a constant, or we add one row multiplied by a constant to another row of our matrix. Okay, so this subspace is a subspace here, and that's why the dimension of, or maybe just, okay, that's why the row rank of the matrix B is not greater than the row rank of the matrix A. But all elementary rows are invertible. So the rows of the first matrix can also be obtained from the rows of the second matrix by elementary row operations. And that's why the span of the rows of the first matrix is a subspace in the span of the rows of the second matrix. That's why the row rank of A is not greater than the row rank of B. And so we get the relation that the row ranks of these matrices are equal, and so this proves the statement that elementary row operations preserve the rank of a matrix. Now I'm going to formulate and to prove an important result on how the row rank of a matrix can be computed. So let A be a matrix with n rows and m columns. Then its row rank is equal to the number of non-zero rows in its reduced row echelon form. So it is not essential here whether this row echelon form is the reduced row echelon form or it is just a row echelon form. So this is not essential. So first of all, let us observe that since the elementary row operations do not change the row rank of a matrix, and reduced row echelon form or just row echelon form is obtained from the initial matrix by applying elementary row operations, the row rank of any row echelon form of our matrix is the same as the row rank of the initial matrix. So let B be a row echelon form of A, since B is obtained from A by a series of elementary row operations. So the row rank of B is equal to the row rank of A. And so let us look at the matrix B and let us try to determine its row rank. So let G sub k be the number of the first non-zero element in the kth row of the matrix B. So here we assume that the kth row is non-zero. So let us look at our row echelon form. We have this staircase structure. And so what is G1? So G1 is the number of the first non-zero element here. Then G2 is the number of the first non-zero element in the second row, and so on. So G3 is the number of the first non-zero element in this row, and so on. So we have this staircase structure, and now let us show that all these non-zero rows are linearly independent. So consider non-zero rows in the matrix B. So these are the first row of B, the second row, and so let R be the last non-zero row in our matrix B. So according to the definition, all zero rows are at the bottom of our matrix. And now I'm going to prove that these vectors are linearly independent. So assume these vectors are linearly dependent. So what does this mean? This means that there exist alpha 1, etc., alpha r, some real numbers such that alpha 1 multiplied by the first row of B plus alpha 2 multiplied by the second row of B plus etc. plus alpha sub r multiplied by the rth row of B is 0. I will, for convenience, I will denote this vector by V, and we will prove that V is 0. And so consider the component of V with the number J1. So since J1 is less than J2, less than J3, etc., less than JR, so this component has the form alpha 1 multiplied by the element of the matrix. So if we look at the structure of this matrix, when we consider the linear combination, when we consider any linear combination of these vectors, we have zeros in all vectors besides the first one here at this component. So the component of the vector v with the number j1 is obtained as alpha 1 multiplied by the component with this number of the first row. So it would be b1 sub j1. So this is the element of the matrix. And we assume that our vector is 0, so this should be 0. But B1 sub J1 is the first non-zero element in the first row, so this is non-zero, and so we get that alpha 1 is 0. So actually we do not have the first term in this relation, so this relation starts with the second term, and in the same way we prove that since alpha 1 is 0, the component of V with the number J sub 2 is just alpha 2 multiplied by B2 sub J2, just because we do not have the first vector in this sum since alpha 1 is 0. And similarly we get that alpha 2 is 0, and so we prove that all the coefficients are 0, and that's why the rows are linearly independent. So these rows are linearly independent, and other rows are zeros. So the dimension of the row rank of B, which is the dimension of the span of rows, is just R, which is the number of linearly independent vectors. And so this proves the theorem. So the row rank of A is also equal to the number of non-zero elements in a row echelon form. So now we have a tool to find the row rank of a matrix. We just need to find any row echelon form of our matrix and compute the number of non-zero rows in this row echelon form, and this will give us the row rank of a matrix. And so the section 5.2 is the column rank. So previously we considered the rank of the family of rows of a matrix, and now I'm going to talk about the family of columns of a matrix. So we will give another definition. Let A be a matrix with n rows and m columns. Then the column rank of n of A is the rank of the family of its columns. So C stands for column rank here, is the dimension of the span of columns of the matrix. There should be an angle bracket here. then the rank, the column rank of A is the rank of the family of its columns, right? Let us prove the following statement concerning the column rank of a matrix. So elementary. Maybe now it will not yet be clear why is this related to the column rank, but it will become obvious later. Elementary row operations. Preserve linear relations between columns of a matrix. So let A be a matrix and let B be obtained from A by an elementary row operation. If a family of columns of A is linearly independent, then the relation alpha 1 multiplied by the first column of A plus alpha 2 multiplied by the second column of A, sorry, not of B, but of A, plus etc. plus alpha sub m times the mth column of A equals 0 implies that alpha 1 equals alpha 2 equals etc. equals alpha sub m equals 0. But let us look at this relation. So this relation can be rewritten in the following form. So here we multiply columns by these coefficients, so we can just rewrite it as the product of the matrix A by the column of alpha 1, etc., alpha m, and this is 0. So, linear system Ax equals 0 has only trivial solution. Right, so if these vectors are linearly independent, then the following relation is satisfied only if all alphas are zeros, and this means that this linear system has only trivial solution. Okay, but the system bx equals 0 is equivalent to the system ax equals 0. That's why it also has only trivial solution. So this means that the relation alpha 1 multiplied by the first column of B plus etc. plus alpha m multiplied by the mth column of B equals 0 implies alpha 1 equals etc. equals alpha m equals 0. So the columns of B are linearly independent. So since elementary row operations are invertible, if the rows of B are linearly independent, then the rows of A are also linearly independent. Assume now there is some relation between the columns of a matrix. So in the first case, we assumed that they are linearly independent, and so in this case, the columns of the second matrix are also linearly independent. So assume there is a relation between the columns of A. So alpha 1 multiplied by the first column of A plus alpha 2 multiplied by the second column of A plus etc. plus alpha sub m multiplied by the mth column of A, not of B but of A, is 0. As we already mentioned, this means that the m tuple alpha 1 etc. alpha m is a solution to the linear system ax equals 0. And so since this system is equivalent to the system bx equals 0, the same vector alpha 1, etc., alpha m is also a solution of the second system, and so we get a relation. Actually, we get the same relation between the columns of the matrix B. So alpha 1 multiplied by the first column of B plus etc. plus alpha m multiplied by the mth column of B is 0. So we see that the relations are preserved, and this is exactly what we need to prove. And as a corollary of this statement, we get the following important result, that the rank of the column rank of a matrix is equal to the column rank of its any row echelon form. So let B be a row echelon form of A, then the column rank of B is equal to the column rank of A, and in particular it is equal to the column rank of the reduced row echelon form of A. So we get this as a corollary because all the relations between the columns are preserved, so we can look at a row echelon form of our matrix, and then we can find the basis in the span of columns of this matrix, and in this case the vectors with the same numbers in the original matrix, in the initial matrix, they will form a basis in the span of all vectors, just because the relations between the columns are preserved when we apply elementary row operations. Now I'm going to formulate and to prove an important theorem that states that the row rank of a matrix equals its column rank. So let A be a matrix with n rows and m columns, then the row rank of A equals its column rank. Let B be the reduced row echelon form of the matrix A. So we know that the row rank of A equals the row rank of B, and the column rank of A also equals the column rank of B. So we need to prove that the column ranks of matrices of the matrix B is equal to its row rank. So the row rank of B is equal to the column rank of B. So the row rank of our matrix is equal to the number of non-zero rows in this matrix, as we already proved. And the row rank of B is equal to the number of non-zero rows in B. And now let us look at the columns of this matrix, and we will prove that columns of B that contain leading elements are linearly independent. So let us look at the structure of the reduced row echelon form. So we have this staircase, and since this is the reduced row echelon form, the leading elements are equal to 1 here in all the rows, and all the elements above the leading ones are zeros. So this follows from the definition of the reduced row echelon form, and we want to prove that the columns that correspond to the leading elements are linearly independent. This is more or less obvious just because we can use the same argument as we used before when we considered the basis in the space Rn. So these columns maybe better say each of these columns has only one non-zero element, and these elements are on different positions. This means that in the first column, this one is on the first position, and the second column it will be on the second position, and so on. So similarly to the example that we considered before, these vectors are linearly independent. So obviously these vectors are linearly independent. And now let us show that all other columns can be expressed as their linear combinations. Combinations of these columns. Indeed, jth column does not contain a leading element. So let me just choose some column of this kind here. So this is the jth column, and let us assume that it does not contain a leading element. So it has some elements here. And the jth column of B has the form, so B sub 1j, B sub 2j, etc., B sub kj, and then zeros. And obviously, it can be represented as a linear combination of the vectors corresponding to leading elements to the left of this vector. So it is B sub 1j multiplied by the column of the matrix B with the number j1 plus B2j by the column with the number B2 of B plus etc. plus B sub kj multiplied by the column with the number jk of B, where j sub l is the first non-zero element in the lth row of B. So we get this relation, and all these columns are the columns that contain leading elements. So this proves that the columns that contain leading elements form a basis in the span of columns of B. Form a basis in the span of columns of the matrix B. But each non-zero column, each non-zero row, of B contains a leading element, and any leading element is contained in some non-zero row. So what do we have? So the row rank of B equals the number of non-zero rows. So the number of non-zero rows equals the number of leading elements. And the number of leading elements equals the number of vectors in the bases in the span of columns. So this equals the column rank of B. So this proves that the row rank of B equals the column rank of B, and we know that both are preserved when we apply elementary row operations. So the row rank of B, so the row rank of the initial matrix is equal to the column rank of the initial matrix. So this proves the statement of our theorem. So now we're able to give the following definition. Let A be a matrix with n rows and m columns and with real entries, then its rank is its row or column rank. So since they are equal, we do not need to specify which rank we consider, and that's why the rank of the matrix is just its row rank or its column rank. So the notation is just Rk of A without any subscript. So we do not need to use subscript since both ranks are the same. And besides this, we have an important corollary that for any matrix, its rank is equal to the rank of its transpose, just because the row rank of A is equal to the column rank of A transpose, and since the rank does not depend on what do we count, columns or rows, so these ranks are equal. Okay, so this is what we need to say about the rank, and now we will discuss one application of the rank. So this would be section 5.3, Rouché Capelli theorem. So this is the result, which is quite simple, but nevertheless sometimes it is used, and that's why we will call this result a theorem. Let A be a matrix with n rows and m columns. Then linear system A equals B, non-homogeneous linear system, is consistent if and only if the rank of the matrix A is equal to the rank of the augmented matrix of this system. So the rank of matrix of coefficients should be equal to the rank of the augmented matrix. So the proof the column x1, etc., xm is a solution to the system ax equals b if and only if x1 multiplied by the first column of A plus etc. plus xm multiplied by the mth column of A equals B. So this is what we already used today in the proof of one of the theorems. So this is exactly so this matrix relation can be rewritten in this form. So this system is consistent if there exists, or maybe if and only if, better to say if and only if there exist x1, etc., xm such that the right-hand side is the linear combination of these vectors, such that x1 multiplied by the first column of A plus etc. plus xm multiplied by the mth column of A equals B. So this is equivalent to the fact that B belongs to the span of columns of the matrix A. That's why if, so there, maybe I'll better put it like this. Therefore, the fact that the rank of A equals the rank of the augmented matrix is equivalent to the fact that B can be represented as the linear combination of the columns of the matrix A. And as we have already mentioned, this is equivalent to the fact that the system Ax equals B is consistent. So this proves the theorem. And now I need to make a terminological remark. So in different countries this theorem is known under different names. So this theorem sometimes is referred to as the Kronecker-Capelli theorem, or Rouché-Fontenay theorem, or even Rouché-Frobenius theorem. So this depends on the country. So this theorem is just an application of the notion of the rank, and we see that the notion of the rank can be used in order to describe the behavior of a linear system, of a linear non-homogeneous system. And so we'll stop here, and at the next lecture we will continue to discuss the properties of the rank of a matrix.